I put some curves here. This is just free. I mean, this is not what we're going to talk about today, but I had some people in the office hours, so I thought about this. So if you think of recall and precision with respect to time, which of these curves can be a legitimate recall curve? And which of these curves can be a legitimate precision curve? Or more importantly, are there any curves that cannot ever be a recall curve, cannot ever be a precision curve?
3.
Which one? What? Say something.
3 for recall.
3
Cannot.
is what? It cannot be possible. Just it's like very simple dimensional analysis, but you may not have thought about this. Your recall can never reduce. Okay, because that's why once you set it, it's out there. You can't take it back. Okay, as you keep giving more and more results, your recall can never reduce. The only thing you can reduce very effectively is your precision by talking junk, right? So it's interesting to know that. I mean, because recall is monotonically increasing, or it's monotonically non-decreasing. It doesn't have to. I mean, between two parts, recall may remain the same, but it can never go back. It cannot come fall down. And you don't see this normally yourself, because what you are actually having is, this is basically recall as a function of time, and this is precision as a function of time, and you essentially got rid of t, and you wrote precision as a function of recall, which is a precision recall curve. Okay, so there you don't necessarily notice that the recall never comes down, but here obviously you will notice. Okay, so please come on. Actually, it's fine. So that's about that. Any questions? Yes.
Number 2 is not possible in precision.
Number 2 is not possible in precision.
Precision can never remain constant.
Precision, that's actually a good point. Precision can never remain constant. It is a good point. I didn't think about that. That's a very good point. Did people get that? Right? Because whenever you say something, either you're saying something relevant or something irrelevant. So precision cannot stay constant. That's a very good point. I didn't think about it. I mean, again, there are many ramifications of what we already know that we don't necessarily compute. And but part of getting a deeper understanding is computing the ramifications of what you already know. I mean, coming to this class, I didn't think that I would write these particular curves. Neither did I think about the fact that precision won't, ever remain constant. It'll either have to fall down or fall up.
But we are making it, plotting it with respect to time.
Yeah.
It's not with respect to number of documents retrieved.
Well, I understand, but even if you consider, time, the only thing we really care about is the number of documents. It's still a very reasonable point. I think it's a good point. Yes?
Precision increase over the time?
What?
Precision?
Precision can increase and it can reduce too.
But should it increase?
What?
Should it increase over the time?
What do you mean, should it increase?
Shouldn't it be like first result should be the most?
No, precision can increase as well as reduce over time, is my point. That, think about like an interview where you started talking sense in the beginning and then slowly started talking nonsense, so your precision went down. You started talking nonsense in the beginning because you're very nervous, and you slowly started talking sense, so your precision went up. But everything you said is out there, so your recall never reduced. Okay? Okay. So what I'm going to do is going back to what we were discussing yesterday before yesterday, on association clusters, which is a way of doing correlation analysis to figure out, to remind you, what we were talking about is, if you think of terms as, documents as vectors in the space of terms, or terms as vectors in the space of documents, then if you want to consider the term-term correlation matrix, then that should be a diagonal matrix, if in fact the terms were truly independent. Okay? And if that's not to be the case, then the non-diagonal entries can tell you something about how closely correlated is another term to this term. Okay, And then, so we were trying to figure that out. And then this point, which we'll come back to later. And so the idea was the simplest unweighted, so unnormalized correlation matrix might be, so suppose I have these three keywords and these are the documents. The unweighted correlation matrix would be, so this is a TD matrix, TD times TD dash, or TD transpose, you'll get me a TT matrix, and that's this matrix. And as I said, the problem with this is some terms are much more in love with themselves than other terms are. And what you really care about is you assume that a term is 100% correlated with itself. Every term is 100% correlated with itself. And if you normalize it that way, then you can actually get a better feel for which terms are actually well correlated with this term. And to do that, what we figured out is basically think of these as the correlation values, the unnormalized correlation values for this is C11, C12, C13, and then similarly C21, C22, C23, etc. Okay, so to normalize them, what I take, let's say to normalize this number, I will just take C12, which is 4, and divide it by C11, C12 minus C12. Sorry, C11, C22 minus C12. Okay, so the idea, one way of thinking about this is really this is sort of what you're computing here is a Jaccard similarity matrix. Okay, so you're computing intersection by union, and when you're computing the union, you wind up, if you take the sizes, then you double count the intersection, so you subtract an intersection. That's one way of understanding. Okay. So essentially, I compute if the original matrix is CUV, the new matrix would be CUV by CUU plus CVV minus CUV. Okay. If I do that transformation, then I will get this matrix. Okay. And so in this case, I had figured out that K1 is most correlated to K3. Now, of course, you don't quite know what K1 and K2 are supposed to be correlated here because you don't know what these terms are. So we go back to our example, for which you do have an idea, right? So this was, remember, your database and statistics example. So I don't do any fancy improvements. I just take direct raw term frequencies in this case, and I just compute term-term correlation matrix, which is this. Okay, and then I compute the normalized term-term correlation matrix, which is association clusters, which is this. Okay, if you see now, obviously what you actually see is the first term, which is database, is most correlated with the second term, 0.77 correlated with the second term. It's correlated most with SQL. That sounds reasonable. Okay, and similarly, the last term, linear, T6, is correlated most with the T5, likelihood. So linear is somehow correlated more with likelihood. And what about likelihood itself? Likelihood is correlated most with databases. No, sorry. It's correlated with regression. Okay, so it's a reasonable thing. So you just basically did matrix multiplication followed by some normalization to capture what you wanted to capture, which is certain terms are actually, they belong together, right? Yeah, okay. So that's that. And so one other piece, since we came all the way here, one other little more improvement we can do is having computed this matrix now. Notice that this is the T1's row, the K1's row, K2's row, K3's row. Right? That's what it was. So the K1 really, what this matrix is doing is, of course, it's doing that term-term correlations. But you can, one thing that we'll do is we'll start looking at everything as a vector. Okay? So now I can think of the term as a vector in the space of other terms, including itself. Right? By sort of abuse of, intuitions. Okay? Now if I do this, now this is my T1 vector, this is my T2 vector. Why shouldn't I compute the similarity between T1 and T2 by computing the vector similarity between those two vectors. You see what I'm saying? Because you did vector similarity, you have two vectors. I just showed you two vectors. Why don't I compute the similarity between two terms, a better estimate of the similarity between two terms by taking the vector similarity between the two vectors corresponding to those terms. Now, if you were to do it, what you get, obviously you get something slightly different from this, right? What does it capture? What it captures is the following scenario. Suppose the first one only captures pairwise correlations. So if T1 is present always in every, if K1 is always present in every file where K2 is present, K1 and K2 are well correlated. Now, if K3 is present in many of the files where K2 is present, then K2 and K3 are well correlated. But then to the extent K1 is correlated with K2, K2 is correlated with K3, K1 is really correlated also with K3. Right? So I have 200 documents, this is from an old times, but they have 200 documents with Bush and Iraq in them. Okay? And so, and then similarly I have 200 documents, additional documents with Iraq and Saddam in them. So, in however small a way, Bush is related to Saddam. Because Bush is related to Iraq, Iraq is related to Saddam, so Bush is related to Saddam. It may well be that there is no single file in my corpus where Bush and Saddam are occurring together. Okay? And yet, they are related. And the term-term correlation matrices that I considered would not have computed this. Whereas when I do one more step where I take the entire T vector, T1 vector, and take the the cosine similarity matrix with the T2 vector. So now the new matrix that I'm computing is I will start with the first there was the unnormalized one, then I got the normalized one, and then the third step, if I want, I can then basically say a new matrix where the ijth entry would be the vector similarity between the Ti vector and the Tj vector. Right? Okay? I can do this. And if I were to do this, so this is called another name, it's called scalar clusters. So here I have normalized correlation matrix, and if I take this vector and this vector and take their, so for this term here, this should be T1 dot T2, so this dot this, dot product of this. Okay, so that's what this would be. Now if I were to do the same thing for my statistics example, so I already have association clusters. Now I basically am going to take each of these vectors and take their dot products and put the ijth element. And then if I were to do this, what happens? So in this particular case, all I found out is that database is most related to SQL, and the second most related to index. That's what we found based on this. And then, and that's like, that more or less makes up for your tuition dollars. That's like the best animation you've ever seen in this class. Right? I no longer know how to do this, but anyway. So in this case, if I were to then take the ti.tj, right? Then I will get a new matrix, which is very similar to this, except notice that database has become even more friendly with SQL. Even more friendly with SQL. So in this example, the friendliest terms haven't changed, but some other example, it might change. Because co-occurrence is sort of transitive. You know, you are occurring with this guy is occurring with this other guy, so in some sense you are sort of related. That's the capture, that's what you're capturing in this. Okay? So the names for this one is called the scalar clusters, this one is called the association clusters. But this is a cute idea. This is a very cute idea for computing correlations between terms. That doesn't require humongous math, because the next thing that I will be talking to you about would be the most technically sophisticated lecture in this whole class, which is latent semantic indexing. Okay? But this one, very easy to do. Okay? So now having come here, the one question of course is, what am I computing these clusters on. So I started here with the TD matrix, the term document matrix. Okay? So in some sense, I'm analyzing the document corpus. Remember I said anytime I can do something with the document corpus, I can also do it with the query logs, if I have query logs. Okay? So here is a slide basically saying you can do this entire analysis over the document corpus, or you can do this entire analysis over the query logs, and both of them will give you useful information. Okay? If you have query logs, probably you would like to then, that basically will tell you that people typing this word also are typing this word. So maybe I should throw this in for you. That's how query completions are done. Okay? Except as I said, query log based analysis does have this cold start problem. If nobody is using your search engine, then you don't have query logs. And because you have no query logs, you don't give good results, so nobody is going to use your search engines. So if you don't have query logs, then a second best idea is at least to, so another idea in this case is to do it on the document corpus. Now when you're doing in the document corpus, there's an interesting question. In some sense it's also true here, but it's even more true here, which is, are you going to do this computation over the entire document corpus? That means the TD matrix now would be, T would be the size of the vocabulary, D would be the size of the document corpus. So million by 8 billion. Okay? Are you going to do it at that level? That would be called global thesaurus construction. By the way, this whole thing is called thesaurus construction because in some sense you're computing functional synonyms for words. Roger's thesaurus basically tells you, given this word, what other words have similar sense. Okay, here you are computing a functional thesaurus, right? So you can compute a global thesaurus this way, and it will be costly, but you do it once and you're done. Or you can compute a local or query-specific thesaurus. How do I do that? This is obvious because you have a document corpus. This one, you run the query first, get the top 100 or so results that you have, and then analyze those 100 documents for term-term relations. So you only do the TD matrix over that. Okay? And then find what are the other words that seem to be close to the query words. And then tell user, would you like to add some of these words to your query? That would be allowing query elaboration, for example. Okay? Now the trade-off between this and this is sometimes with respect to a specific query, there may be stronger correlations between two words, which kind of go away when you look at the entire document as a whole. Okay? So for example, with respect to computer science queries, the word operating is very friendly with system. With respect to the universe, operating is probably just as friendly with room, operating theater, military operation, something or other. So the connection between operating and systems is gone when you look at the entire document corpus. It's not any stronger than in many of the other connections. So the thesauri also will change, right? Based on whether you do it locally versus globally. Yes?
So when you do the scalar in the previous slide,
Mm-hmm.
you still get the computer science versus operating system, or you don't look at the other words?
Well, I didn't understand what you said.
I guess I don't understand from this to that.
Oh, from this to this. So for example, if I want to get this number is 1, 2, right? Element 1, 2. So I take the first vector and the second vector, take the dot product. Take their cosine theorem similarity, which is dot product divided by their normalization factor.
So essentially that is this matrix square.
What?
That one is this one square.
No, you also normalize. Yes, it's true. That's connected, but it's essentially, in your case, you take this vector and this vector, take the cosine theorem similarity. That's what that number is. And the connection that he's making is, as you keep, how many of you remember how to compute transitive closure in the 310? Transitive closure involves starting with the neighborhood matrix, keep multiplying it by itself. As you keep doing this, you get transitive closure matrix. So that's the connection he's making. One way of getting transitive closure is keep multiplying the matrix by itself. Okay, that's good connection, by the way. That's what you should be doing. Connect everything to everything. That's the only way. Unless you have like a brain paralysis, everything will stay. Whereas if everything is a different piece, they'll just slowly fall through the seed, of your brain. Okay.
So,
Okay.
I'm having a difficulty understanding this. Is that you take the first row and you take the second row, combine, get the cos theta, cos product, dot product of it, and that becomes the first term, is it there?
No, all I'm saying is this is a matrix, right? This matrix has ijth term.
Yeah.
So ijth term of this matrix is the vector similarity between the ith row and the jth row in this matrix. Okay?
So ij term is equal to ji term.
It will be, obviously. I mean, correlations are symmetric, unlike friendships. Or love, unrequited love, for example. Okay. Okay. So, so that's basically your document corpus and query logs aspect. And then remember that you could do in either of them. And in fact, one of the interesting things is this analysis could be used to get the effects that you have seen in multiple places. The one that I was trying to show you last time was when I typed Sushavande in my Gmail, and I did this in fact just before coming to the class last time. It would say, consider including Yuheng and Raju and Rohit. Not because, the only reason it did this is because it basically realized that in the mails I send, I tend to send mails, whenever I put this guy's name, these guys tend to be, co-occurring together. So it did a co-occurrence analysis. Okay? So now this is across from, IR to, email completion. So, now, suppose, I was thinking all this while about, correlations between terms and documents. So documents are bags of terms. And then I was computing the term correlation. And I can say email messages are bags of addresses. So then I can compute the address correlation. Okay? I can also do the following thing. Amazon users are bags of purchases. Right? And so they can actually do correlations between purchases. And then say, people who are buying this thing are also buying this thing. So would you like to buy it? If you do that, that's collaborative filtering. See what I'm saying? It's the same idea. Again, it comes under different names, but the technology is basically the same. So in the case of collaboration filtering, which we'll again talk about a little later, basically what we're doing is, you're thinking in terms of, instead of documents, you're thinking of users as bags of their purchases. Products are the words, okay, and users are the documents. Okay, using that, you compute product correlation matrix. Okay, that way you can tell people, if you're buying these products, then people like you who buy these products also are buying these other products. Why don't you buy? Okay, so the idea is the same, essentially. Okay, collaborative filtering is highly connected, essentially the same idea. Okay, so that's about term-term correlations and basically correlation analysis, which is a very useful thing because you are able to get through this aspect of if the terms are not independent, can we then exploit their correlation? Notice that if the terms were independent, you would not have, to know that a language is English redundant. Any language which has a thesaurus is redundant. Do you understand what I'm saying? In a non-redundant language, there should be exactly one way of saying everything. In every one thing that you want to say, there should only be one way of saying it. Okay? If there is a thesaurus, that means there are 10,000 ways of saying the same thing to confuse people. Okay, and so English obviously is redundant, and so you can talk about, Roger can actually write his thesaurus. And our documents were obviously, redundant in the sense they have correlations, terms have correlations, and so you can then compute term correlations and figure out functional thesaurus for your vocabulary. Okay, now when we saw this slide before and we didn't look at this part, which is that if in fact terms were independent, then they won't be correlated. If they are not independent, they would be correlated. And here's the interesting thing. Now we started with lemons because we made this huge assumption that documents are vectors of terms and we can use dot product, similarity, etc., etc. All of that theory depends on the terms being independent. Okay? But then we found that the terms are not independent, and rather than just lose hope, we said, well, we'll make lemonade with it. We'll actually figure out exactly which terms are correlated with which other terms. They're not independent, but this will help us tell which are correlated with what terms. Right? That's what we did. Okay. So, but actually we did solve the original problem we had, which is our assumption was that the dimensions are independent, vectors in an independent dimensional space. Okay, so now I will ask this different question, which is, if in fact it's not a diagonal matrix, that means if I take TT matrix, it's not diagonal, that means the non-diagonal entries are not zero, that means terms are not independent, right? Then the question is, can I not produce by change of access a new set of terms which are independent, such that both the documents and the terms that I am talking about are really vectors in this other space? I said this is the most technically sophisticated thing you have to do, and we will do this basically, which is we are now talking about this possibility that both the terms and the documents are really entities in some other space, where the dimensions of that space, the basis vectors, are actually orthogonal as well as linearly independent. So it's an orthonormal basis. So why can't I find a new orthonormal basis to this space? If I were to do that, then I will actually figure out what are the things that are being talked about in the various documents. And you don't need to worry about correlations anymore. You're thinking of, in some sense, you might say, well, I made the lemonade already, won't I lose it? Well, you made lemonade because you got lemons. You don't need the lemons. It turns out that, in fact, having independent dimensions would be much more helpful in terms of actually computing, real similarity between documents. Okay? That is what we will actually explore starting today till probably, part of or most of next week. This is basically this idea called dimensionality direction. Okay? And some of you probably know about it, some of you don't. So I will lead you through it, like a bunch of examples, and then finally get through how to do it, for linear dimensionality detection. Okay? Okay, so bear with me as I go through crazy examples which may have no connection to this course, but this one actually does. So, suppose I start with documents described in terms of just keywords U and V. Suppose, my document corpus is made up of documents, only the words U and V. My document corpus, basically, my vocabulary was just U and V. Suppose I have that. Okay? So, suppose I had some number of documents, D1 to Dk, which are these. U and V as the original words. Okay? Up to this, it's fine. Now, suppose a bunch of new keywords were made up, where, a keyword called W was made up, where W is nothing but 2U plus 3V. So, for example, if this document had UUV previously, okay, that means it has 2 U's and 1 V, okay? That's the document before. Okay, now after this, I'm introducing a new dimension, W. So for an outsider, W is now an extra dimension, so the documents now are 3-dimensional. Except you and I, the malicious people, know that W is really nothing but 2U plus 3V. So I would just say this would be what? 2u plus 3v is 4 plus 3, 7w. So this document, UUV, has now become UUV and 7w's. So the documents have changed. Suppose I do this. Okay? Will you be able to, and I give you these documents. Notice that the original documents actually they were living in a two-dimensional space. They only had u and v. Now I give you these documents. Up front it looks like they live in a three-dimensional world. Right? Now, they don't really live in a three-dimensional world. It looks like they are, but in fact, if you knew this, you can figure this out. But I didn't tell you, I did this, without you knowing it, or at least you have a friend that you're trying to trip up. So we now give your friend these documents. Could your friend figure out that the document she is given are really two-dimensional, not three-dimensional? Think about this, okay? Don't have to answer, just start thinking about this, okay? Next. Suppose after doing this, I think the friend somehow figured this out, let's say. But I want to make it even harder. I would say W equal to 2U plus 3V, maybe they sort of figured out that there's some kind of a correlation in these W's and U's and V's, in particular this linear dependence. Somehow they figured this out. I want to trip them up even more, okay? And I will say, actually, W equal to 2U plus 3V plus epsilon, which is a Gaussian noise, some noise. So every once in a while I'll add an extra 1 or subtract an extra 3 or something, which is a random variable, hopefully from a zero mean Gaussian. Now, can your friend figure out that the files that she was given are two-dimensional, not three-dimensional?
It's easier.
What?
It's easier now.
What?
It's easier now.
No, it's not necessarily. Think about this, okay? So because the noise can actually, your hypothesis that you have about what the connections are might be tripped up by the noise, in this case. You will never be able to find a simple rule plus noise. Now, of course, once I allow you noise, everything can be noise, right? So how do you decide which one is noise and which is not noise? Okay, so can you tell that? It's not enough. I want to go further. Suppose further, at this point, so basically by this time what I would have had is 2U plus 1V plus maybe 7.37W. Right? Because I added like a 0.37 error, noise. Right? Okay. And remember that I'm talking mostly about W, but really I'm adding a whole bunch of them. A bunch of new keywords of the form 2U minus 3V or 4U plus V, etc., etc. So I made a whole bunch of extra keywords. So in fact, this, originally two-dimensional document might have many extra dimensions. So it looks huge, big dimensional beast, but really it's a two-dimensional beast. Knowing that obviously should be easy, because remember I told you that our intuitions about high dimensions are bad. So why would you want to think of everything being in higher dimensions when it is actually in a lower dimension space? Okay. Now, and then so in this case, after this noise addition, then it is 7.37W plus 8.34Q plus blah blah blah. So the extra terms. All of them with linear dependencies plus noise. And then the third, final malicious thing I do now, I get rid of U's and V's from the document. So now I will actually be defining this document. This document now will be just defined as 7.37W plus 8.34Q plus 4.79J, etc. So the original dimensions that these guys were living in are gone. Those dimensions were probably orthogonal to each other. The new dimensions that you came up with may not even be orthogonal. They may not be a basis, first of all, and even if they're a basis, they may not be orthogonal. Okay, now can your friend figure out that looking at these documents, what you are really giving her are these documents? Notice how many things she has to do. First, she has to realize that the terms in the document are really not the final terms making up the space. They themselves are vectors in the original space. Because each of these are vectors in the original space. And that's the only thing left now. The reality is gone. Only made up terms remain. And she has to figure out the noise part. And she has to figure out the dependencies between these terms. So in some sense, what she needs to do is go from here to here. Can she do this? And why should she do it? There are two issues. Okay? Why should she do it? Of course, she should just change friends so that they won't be messing around with people like this, right? Now, why do we want to do this in our problem? Because the fact that keywords in the documents are not actually independent, and that they have synonymy and polysemy. That means keywords might mean the same thing, and some keyword might have more than one meaning. Okay? Can often manifest itself as if some malicious oracle like yourself started from untouched true document and did all these manipulations and gave you noisy data in the wrong dimensions. Okay? And to really get to the truth, you have to get back to this. Do you understand what I'm saying? So it looks like a very weird thing to do. Why, make my life so much harder? But to understand dimensionality reduction, this is what you need to understand. The dimensions that you are watching may not be the dimensions that are actually the relevant ones. Notice that dimensionality reduction is connected to some idea called feature selection idea, which is I'm defining you in terms of a bunch of features, and I might want to know which of these features are important. Feature selection is actually easier than dimensionality reduction, because in this case I can't say which of these terms are important. In fact, all of those terms are derived terms. The real terms, the truth, is here. You won't be. So dimensionality reduction changes the vocabulary. It looks for the real vocabulary under which there is basically independent dimensions, orthonormal basis for the data. Okay? The point that you can be even more meaner to your friend, and the way you could do this is you will say W equal to 2u squared plus 3 log v. If you do that, you then have done nonlinear transformations. Nonlinear transformations on the original data. And then you're trying to figure out the original dimensions. That's much harder. So even for right now, in fact, we won't talk about nonlinear dimensional reduction. But a real dimensional reduction might also be nonlinear sometimes. Okay? So we will be talking about, assume that linear changes are being made, and can I reconstruct the data back? Yes, sir.
Sir, can you give an example where this happens?
It's happening all the time. Every document you pick, it's happening.
A real example.
Computer science. Why do I need computer and science? If I'm always saying computer and science together, why do I have to put computer as well as science? Okay? Convincing yourself that this happens is half the battle. Okay? And because you are in denial. You want to both, not just you, all of us are in denial. We want to both say that the terms are independent and complain that they are not independent. You can't have it both ways. If they are not independent, then you are in this kind of a problem. You may not have all the maliciousness here, but essentially, what I'm going to tell you is one technique that handles all of these together. So, everything else that I did about correlation analysis is just a special case of dimensionality reduction. Okay? You may not do it because the world at large doesn't do smart techniques most of the time. Because they'll hire people like us who would then just basically find exponential approximations to polynomial time problems and execute them. And then it's so that. But in this course, we are actually trying to understand actually what's the right way to solve the problem, and then we may give up. Remember, did I already say this, that the difference between computer science and a hacker is computer scientist knows what's the right way to do it, and then gives up on it. What the heck? I'll do the correlation analysis, which seems much cheaper to do. Okay? But it's nice to understand this because it improves your conceptual understanding of all the issues that you would be repeatedly looking at here. Okay. By the way, I will answer questions, but as you are thinking about it, this will stay with us for 3 classes, probably 2.5 classes at least. As I said, it is probably the most sophisticated topic that you will be doing in this course, and it will need some time to sink in. Okay. So don't worry if you don't get it right away, but do think about, make sure that you understand things. Okay. Yes.
So I understand you're trying to see the correlation when you give these equations, but why do you have to add the noise? I mean, what does it actually mean?
Because I can do noise. Because if you are writing your if you are writing your documents, let's say, you might add in extra words which have no connection to what the document is really about. Why did you do it? You did it. I didn't make you do it. You just did it. So noise could be present. If it's not present, your problem would be somewhat easier, but it can be present.
So you're saying terms which are not related, but still implicitly or explicitly put in documents just to confuse others.
Yeah,
That's the sense.
and it's not that people are being malicious. People are just writing stuff in their documents, and the generative model. You think about this generative model. The generative data model is there is an actual matrix, and then there was an error process that was done where errors were introduced. Okay, and then some omissions were done. Like basically noise was introduced. Okay, and then what you get out, from what you get out, can you get back the original matrix? That's what we are looking at. Okay. Change of topics. Fish. You don't want fish? Yes, go ahead.
We are just looking for a way to represent the data independently, right? With the terms.
What? I want to know what is the true dimensions of the data. I mean, you should be basically, this was the true dimensions of the data. I mean, remember, much of science is like this. We see currently some background noise in the universe. And using that, we try to figure out that there was a Big Bang at some point of time. Okay? So I want to know what were the U and V, what were the original Big Bang dimensions, given the data that I currently have. Except, in the case of Big Bang, etc., these things can be hugely nonlinear transformations. What is left over could be nonlinear transformations. I'm only looking at linear. Wait for a second. Okay, let me continue. I know that this is a tricky topic. Let me continue some more, and then you can take more questions. Okay? Okay, so fish. Right? I have fish. And I'm going to represent fish in terms of 2 features. Documents were represented in terms of 2 words, U and V. Here I'm representing these fish in terms of 2 features. The length of the fish and the width of the fish. I'm a vegetarian. I don't care. I don't care about things like taste of the fish. No. Right? So length of the fish and the width of the fish. Right? And so now I went ahead and I got a whole bunch of fish. I went and caught some bunch of fish in the Tempe Town Lake. And I plotted them in this XY axis. The length axis, the width axis. Each fish is a point in this space. So those are my fish in this space. The question is, are they 2-dimensional fish? I mean, in the sense, is this data really 2-dimensional? Or is it really 1-dimensional with maybe some noise? Start thinking about it. And second question is, suppose too many features, length and weight for a fish, just too much. I want one feature for the fish. Tell me which one can I remove, or which one can I keep?
Volume.
Why should I remove? So if I were to remove this, right, then what do I get? I'll get all the fish on this axis. Basically, if I remove the x-axis, then I get the y-axis projection. If I were to remove this, I'll get the x-axis projection. Is your best idea of these fishes is to project them on either x or y-axis?
Make a new axis.
It really looks much better if the axis were like this. And if the axis were like this, that won't be size, and that won't be length, that won't be width. That's length plus width axis, which is called size. I just made up. You understand what I'm saying? Okay? So if I were to have this data, and if I'm trying to reduce the dimensionality, For the heck of it, I don't want too many dimensions. Sometimes you don't know what is the true dimensionality of the data. All you can tell is, I just have too many dimensions. I'll reduce some. The question is, what am I going to reduce? Okay, now feature selection will say, remove my x or a y, one of them. But the true dimensionality reduction first should check, are x and y correlated? In this case, are x and y correlated? How many of you think it's not correlated? Raise your hands. How many of them think that it's not correlated? More people said no, but I think only one guy is actually brave enough. And how many of you think they are correlated? Okay, tell me why they are correlated. That guy. Why do you think they are correlated?
It's a linear approximation.
So what does correlation mean? The point is, if I were to give you the x-axis of a fish, do you know something about the y-axis of the fish? That's what correlation means. If there's no correlation whatsoever, how would this picture look? It'll look like a rectangle. Points all over the rectangle. The fact that it's not a rectangle, the entire rectangle is not filled, it's only a piece of the rectangle that's filled, means they're correlated. It's almost as if there is some sort of an ellipse living here and all the points are within that ellipse. And the ellipse metaphor is not bad. In fact, we'll get back to it in a minute. Okay? So the correlation essentially means, in this case, x and y are correlated. So asking should I remove x or asking y is like asking should I remove your right eye or left eye. Okay? So the Sophie's choice can be converted by changing the dimensions. Essentially, in this case. Okay? So what I would do is, if I were to essentially realize that the best axis for this is this, and then take the orthogonal axis to that would be my two x and y dimensions. They would then be maximally uncorrelated. And in that case, you can then pick, if you want to pick only one dimension, you can decide which one to pick. So for example, suppose I want to tell you these are my new dimensions, this and this. Now I want you to keep only one dimension. Which would you do? Keep the, would you keep this or this? Keep this, right? That was obvious now. What were you doing when you did that?
Spreading
Why
out
was it so obvious? Somebody said spreading.
Spreading out the data.
Exactly. Variance. What you want to do is basically find the new axis such that the new axis the first axis would capture the maximum amount of variance in the data. So which direction is the data most spread out? Then the second axis should be an axis that is perpendicular to the first axis and it captures the maximum remaining amount of variance. And the third and so on. If you do this, in fact, one of the beautiful things is because the dimensions are correlated, you don't need to worry about, if I want to pick k dimensions, I just pick the top k dimensions. Why is this a good thing? Why are you supposed to feel good that if I want to pick k dimensions, I just have to pick top k dimensions as against anything else? What else could you have been doing? Yes?
Having to take every single word in the English language.
Not just that. The issue is, remember, so in IR, right, if I rank each document in terms of the similarity to the query and just take the top k documents, would that be correct way to do IR? We said it's not. We said we have to consider diversity. We said we have to care about that once you compute the first document that's most similar, the second document should be the one that is most distinct from the first document that is most similar to the query. You have to consider the residual increment. When you are considering orthogonal axes, you don't need to consider residual because you already made sure that the axes are orthogonal. This is all jumping ahead. I'm assuming that I have a rich uncle who will finally tell me, mathematically sophisticated uncle, who will finally tell me how to get orthogonal basis for this data, in which case I can then do dimensionality reduction very easily. You want to reduce the dimensionality to k dimensions, I'll just pick the top k dimensions. You see what I'm saying? Okay, so continuing with this example a little bit more. So if I am allowed to start messing around with the origins, in this case, just shifting the origin itself is pretty good, right? But that's not enough. Really, what you want to do is you also want to rotate the axis. And furthermore, it's better if once you get this axis, the other axis is perpendicular to it, because then they would be truly uncorrelated, and the maximally uncorrelated. Okay. Now, so what should this? If I were to have this as my new axis, does it have a name in terms of the old data? No, because in the old data, x-axis was length, y-axis was width. This is length plus width. You guys think length plus width is size. But when I said 2u plus 3v, you said that's not a word. I mean, u is computer, v is structure, and 2 computers plus 3 structures, I decided is a word and you didn't know what it means. In general, a linearly transformed word may not have any meaning that you can easily associate with if you are starting from the original features. This fact that this can be seen as size, it's just because we are smart. We can decide, that, length plus width, let's call it size. If you can do that, I'll say 2u plus 3v, let's just call it W. That's what I'm doing. The names don't matter. Names never matter. Right? If names matter, then your programs will die right away. They're just, vectors in some random space. Right? Okay. So I would then say, if this is the original space, I would call it some other space. It's a factor space. Okay? And I use the word factors because in latent semantic indexing, that's what we do. Okay, so you're going well actually. So you can, what if, so as I said, if I only compute the dimension size this time, then I'll argue that I have captured the maximum amount of variance I could possibly capture by just picking one linear dimension. And you ask how much? Well, it turns out that if we take this matrix, this data is, can be seen as a matrix, and I can do eigenvalue decomposition, eigenvector decomposition. Eigenvector decomposition can be thought of as putting a nice little ellipsoid over the data. In 2 dimensions, ellipsoid will be ellipse. In 3 dimensions, it will be an actual 3-dimensional ellipsoid. And n dimension will be n-dimensional ellipsoid that you can't visualize. Okay? So an eigen decomposition basically can be seen as putting an ellipsoid around the data and taking the major axis and the minor axis. Okay? If it's a 2-dimensional ellipse, they will only have 2 axes. If it's 3-dimensional ellipse, it will have 3 axes. If you have 4-dimensional ellipse, there will be 4 axes. So these vectors that you're getting, eigenvectors, those are the major axis, next major axis, and so on. Now, if I were to take this data and I do the eigen decomposition on this, then I will get this as the major vector, this as minor vector. How do I know which is major, which is minor? The major one has the bigger lambda. The lambda is really the size. 1.75 is the first eigenvalue, and 0.25 is the second eigenvalue. And 1.75, so the eigenvectors tell you the new dimensions. Eigenvalues tell you the importance of those dimensions. So now if I have to pick the top dimension, I pick the one corresponding to the highest lambda. If I pick 2, I pick the first and the second. So just basically, sort the dimensions in terms of their eigenvalues and pick them, until I'm done with eigendimensions. Okay. So in this case, this is 1.75, this is 0.25. Now, what's interesting is if I were to just pick this thing, then I can actually give you an expression about the amount of variance in the data I lost. Amount of variance in the data I lost. One way I can lose, the whole point of data compression really is, dimensional reduction is a kind of a compression technique. Right? I don't want to compress in such a way that all of you look alike to me. Do you understand what I'm saying? I want to remove some of the irrelevant features, such as some of you have longer hair, some of you have shorter hair, some of you are full sleeve, some of you are non-full sleeve. But if I just keep reducing the things to an extent that basically everybody is just one-dimensional, part of the fun, then I can't actually differentiate any variance among them. Currently, you're all unique. You're all sitting in different places, you have different clothes, etc., etc. But the question is, what fraction of the variance in the data would I lose if I were to project away this dimension? And there's a nice little expression. It turns out that that's nothing but this eigenvalue divided by the sum of all the eigenvalues. So if I take top k eigenvalue, top k dimensions, then the variance that I'm able to capture with that will be the eigenvalues corresponding to those k dimensions divided by all the eigenvalues. That's the fraction that I'm capturing. So 1 minus that is the fraction of variance that I lost. I understand variance isn't something that you can feel excited about, but you do know that if the whole variance is gone, that's like saying entire document corpus is just really the same. Whatever your query, I'll give you some document. Okay, they're all the same. At that point, you have taken your dimensionality reduction to many steps too far. You see what I'm saying? Okay? So in this case, if I, for this particular data, it turns out that if I just discard this axis, then I will only lose 12.5%. 12.5% of the variance. Okay? Now, do you see the connection between this and the documents that we are talking about? Size and the length and width are like words of the document. Fishes are the documents, they are made up of features, length and width. And each fish is a point in the space of length and width. Each document was a point in the UV space. In fact, actually what you see, by the way, is the fishes that you saw are not in the UV space, they are in this space. Notice what makes you realize that there is noise here. It's not actually one dimension. In fact, the dimensionality of the data is still 2 full dimensions. It's just that if you only keep the one dimension, you only lose 12.5% of the variance. That's the noise, in some sense. Okay? Had this been truly one-dimensional data and no noise was present, then what would happen is all these species will nicely line up on this red line. And so you don't have to ask, what about the other dimension? There is no other dimension. You don't need to worry about losing variance. So this is a scenario where really it is kind of a close to one-dimensional data with just a little extra variance left over in the second dimension. So, yeah.
If we have a circle, we are screwed, right? If we have a circle instead of an ellipse, we are screwed.
No, this, that's, well, yeah, actually, interestingly, it turns out that eigenvalue is one of the, ellipsoid, circle is an ellipse, right? And so, what the problem with the circle is that it's basically its major axes are all the same value. So that means all of them are equal variance. It's not necessarily that. That basically means that's a true two-dimensional data. That really is a true two-dimensional data. Okay? But one thing that we will talk about is, now that this is the first time in the class, formally we talked about eigenvalues and eigenvectors. If you consider the eigenvalue lambda1, consider the eigenvalue lambda2, subtract one from the other, that's called the eigengap. Okay? And it turns out many things, the efficiency of many algorithms depend on the eigengap, for example. Okay, so remember in the homework 0, you took a vector and you kept multiplying it with this matrix and then resizing the vector to unit vector. At some point of time, assuming that you've done this, if you didn't do this, you missed the beautiful experience. If you did do it, you would have found that irrespective of the vector you started with, in the end you ended with the primary eigenvector of the matrix. The question is, you are guaranteed to end with the primary eigenvector of the matrix. The question is, how many iterations do you have to do before you get very close to the primary eigenvector? That depends exponentially on this one. If the lambda1 minus lambda2 is high, with just a few iterations you would already have gone to the primary eigenvector selection. If they're very close, it will take forever, but you will get there. Okay, so fishes are done, and the last thing I want to do today, and hope that at least some of you will show back up next class, is if you can do it for fish, why not for documents? Okay? In particular, we have documents as vectors in the space of terms that have been given, but we don't really believe these terms are the true terms. We want to find the true terms. Like, for example, we were given length and width as the terms, but the true term is size and whatever is left after size. Notice that, in fact, I don't even have a name for this guy. What the heck is this guy? I don't know what the name is. I could say this is size. X plus y is size. What is x minus y? I don't know. It's not obvious. The point is, these dimensions may not have to have any names that you can understand. It's just a linear combination of the old dimensions. Okay? So the question then is, the current terms are, it's like this is the religious person's dream come true. Everything we see is illusion, and we spend our lifetime trying to figure out the true reality. Okay? And what you see, the documents you see in front of them are just illusions because they've been corrupted out of, linearly corrupted. Okay? But engineering is, you don't need religion, you just need engineering because the entire world is corrupted. The audio that you get is originally produced as a noisy audio, and then you filter the noise out so that you can hear the quote-unquote reality. Okay, so we're trying to figure out a filter that will get back the true dimensionality of this data. So transform the axis so that the new axis should have the following properties. Okay, the new axis of the data should have property 1, they should be orthonormal. And that's why, just one class before I sent this mail to the blog, knowing that nobody will read this. But it's, you go back and read it to make sure that you understand the whole linear algebra of basis, spaces, orthonormality. They're all important. Okay? So you want an orthonormal basis. Okay? And then, so that means, remember that the new fish axis are like maximally uncurvated. And then, once they are orthonormal, then they can be ordered in terms of some amount of variance each of them capture. And in some sense, that should be something related to the eigenvalue. I kind of gave away some part of the answer. And then in that case, finally, I can pick top k dimensions in this ordering and use these new k dimensions to do vector space similarity ranking. That's what I want to do. Why is this useful? Why the heck would I want to do it? Unless I'm really paranoid. Well, the reason is just because you're not paranoid doesn't mean they're not out to get you, right? That's the old car, the bumper sticker. So just because you think documents are made by nice people, there's nothing bad with them, doesn't mean that they don't have noise. Nice people can generate noisy documents. Okay? So why? Because it can reduce noise in the documents. It can eliminate dependent variables in the documents. And by doing that, it can capture synonymy and polysemy. If it turns out that computer and science always occur together, it really is a new word called CS.